In class we were able to talk about the motivation for the potential equation as being the equilibrium or steady state solution for both the wave equation and the heat equation in 2 dimensions, as well as in higher dimensions. We'll deal with that later. And we talked about how we had, in general, we could have boundary conditions on all 4 edges of a rectangle. But we're going to focus on the case today where at x equals 0, the boundary, we have our function equals 0, and at x equals a, we also have the boundary that the function equals 0. So at the boundary at x equals 0, we have our function equals 0 is one of our boundary conditions, and at x equals a, we have our second boundary condition. Whereas for our boundary when y equals 0, we have a function, an arbitrary function, and when y equals b, we have a second arbitrary function. And we want to be able to solve this. We're going to use separation of variables. We've got a homogeneous partial differential equation, and on our boundaries for x, we also have homogeneous boundary conditions. So we're going to be trying a separation of variables solution of the form a function of x times a function of y. Let's look at what our partial differential equation becomes. When we take 2 partial derivatives with respect to x, we will be taking 2 derivatives of the x function, but nothing happens to the y function. When we take our 2 partial derivatives with respect to y, we will be taking 2 derivatives of our y function, but nothing will happen to our x function. Consequently, our potential equation becomes 2 derivatives in x times the function of y plus the function of x times 2 derivatives of y, and the PDE says that that should equal 0. So that's our partial differential equation. In our separation of variables strategy, what we want to do is we want to group all of our x terms and all of our y terms on opposite sides of the equation. I might do that by moving the x, y double prime to the other side. And then I could divide both sides by x and y. This is motivated by what we've done earlier. We want to have our y move to the other side, so we get x double prime over x and y double prime over y on separate sides. This gives us our separation of variables equation. So notice on the left I've got x double prime over x, on the right I've got y double prime over y, and the y term has a negative sign. This is going to be important. When we do our separation of variables, recall once we have an equation of x on one side, y on the other, or any other variable, this means that we must have both of these are equal to some constant. And we want to be able to solve this. And we could have put the negative sign on either side. It could have been negative on the x terms. But because our homogeneous boundary conditions were for x, we want to use our knowledge of what we've done before. So that's my motivation. I'm going to leave the x double prime over x as usual because my boundary is on x. If I was solving for y homogeneous boundary conditions, it would be more natural to put the positive sign on the y double prime over y. So let's recall how we do our separation of variables. Once we have our separation equation, we need to remember what our purpose was. We're trying to find non-trivial solutions, right? X times y, non-trivial solutions that satisfy the homogeneous portions. We've got our boundary at the left, our boundary at the right, and our partial differential equation are all homogeneous. And we're going to use superposition to satisfy the other boundaries. Let's focus on our homogeneous boundaries. So we've got when x equals 0 and when x equals a, this function should equal 0. That corresponds to x of 0 times y equals 0, and x of a times y is supposed to equal 0 on those boundaries. but we want x times y itself to be non-trivial. And so our consequence of that is our boundary condition becomes just in terms of x. Once we have our boundary conditions for x, I'm going to solve for a non-trivial solution of x double prime over x as a constant with these boundaries. All of our experience so far tells us the only way we're going to do this is if I get sines and cosines. Specifically for zero boundary conditions, I want sine. That is, we're going to be using our x function is going to be sine of n pi x over a, which means that this constant that we were solving for is the square of n pi over a. And I forgot to say the negative sign. So our differential equation for x, we'll call this our lambda squared. Right, so this is our lambda squared. X double prime plus lambda squared x equals 0, and our equation for y will become y double prime minus lambda squared y equals 0. And I don't have any conditions on my y, so I'm going to be using exponentials there, right? So our y formula, we could have any coefficient, let's call that c1, e to the lambda y. In fact, let's fix that. That should have been a y. So we want y as a function of y is c1 e to the lambda y, and our other formula is e to the minus lambda y. We can have any linear combination of those, and that lambda is our lambda n, so we have our functions. Now we can have any linear combination of these, and we're going to be looking for special forms. Remember, sometimes we've used sinh and cosh, our hyperbolic trig functions, and so we're going to be doing something similar for this problem. So here's where we are right now in our separation of variables. We had our differential equation for x with a x double prime plus lambda x squared x. We had our differential equation for y, y double prime minus lambda squared y. Because of our boundary conditions for x, right, x of 0 has to equal 0 and x of a has to equal 0, we knew we needed sine of lambda x, and the lambda, in order to meet both boundary conditions, was n pi over a. We also know the form of our equation for y, right? We have linear combinations of e to the lambda y and e to the minus lambda y. What we haven't done so far is we haven't taken into account our boundary conditions for y equals 0 and y equals b. What we want to do now is think about what our superposition would look like. And so let me write down our Fourier series expansion. So when the Fourier series is written in terms of our y functions as being an arbitrary function in the span of the exponentials, I have a summation over all possible n's, right? N can go from 1 to infinity, of the x function times an arbitrary y function, and I have two unknown coefficients, c1 and c2, for every n. Maybe I should have had that with an n in my formula, right? So there's c1 for my n and c2 for each n. And where do those coefficients come from? Well, those coefficients come from using my second boundary, that if I were to evaluate this function u at x with y equals 0, I get a formula. The sign is still there, n pi x over a. And when I set y equals 0 in my expansion, each of these exponentials is e to the 0. I'm going to get a product of c1 for n plus c2 for n. And if I evaluate when y equals b, I'll get something similar. Let me pause and write that all in. So that when I evaluate at b, my exponentials are still there. I have c1n times the exponential e to the n pi b over a, and in the second term c2n I have e to the minus n pi b over a, and these are somehow supposed to match my two boundary functions, right? So I've got the function f1 on the bottom and f2 on the top. My goal is I'll be finding Fourier representations of these functions, right? I'll find the Fourier expansion of f1 and of f2, and I'll be needing to solve a system of equations, and this system is going to take a little bit of work. That extra work comes because of my choice of the basis for this two-dimensional space. When I solved it in terms of the exponentials, I'm going to have to solve a system of equations. The reason we liked using sinh and cosh is the sinh of 0 is 0, and I'll be able to simplify some of my terms, and the cosh of 0 was 1. So I might try using sinh and cosh. So let's write down the expansion if I did that instead. So if I were to think in terms of my hyperbolic sine and cosine, again I have an arbitrary coefficient, c1 and c2. There's a different one for each n. So I have c1 times cosh, lambda is n pi over a times y, plus another constant sinh of lambda y. And if I evaluate this at 0, the cosh has a value of 1, and the sinh has a value of 0. So this term, the second term, doesn't even appear, and I've got a single coefficient, so I have c1n times the sine, and so this is just a simple Fourier expansion. I can match my boundary function f1, which has a Fourier expansion, and my coefficient is the ordinary Fourier coefficient of that first function. Unfortunately, if I use this expansion at y equals b, it's a little more complicated. This time, both functions are now non-zero. I happen to know c1n because I solved it in the original f1 boundary, and so if I think about the Fourier expansion of f2, I can solve for this second coefficient using the original coefficient, but there's still a little bit of work involved. I have to do a little bit of solving. So, turned out there's a clever choice for my functions. Instead of using cosh and sinh, I'm going to use a slight variation. The choice I'm going to use is I'll keep sinh because that has a value of 0 when y equals 0. But what I'm going to do instead of using cosh is I'm going to use a shifted sinh function. So notice what's different is it's still n pi over a, but instead of y it's b minus y. Okay. Now this might not feel like it's still in the same linear combination. So what I want to do is I want to show why it's in that same linear combination. But notice what happens. If I substitute in y equals 0, my first term, the sinh of y, becomes sinh of 0, and we know that that equals 0, so this term goes away. And our second term, if I substitute y equals 0, this simplifies to just the sinh of n pi b over a. I get a single term. And so if this is supposed to equal my f1 function, and I've included a Fourier expansion for that function, so we calculate the Fourier coefficients of f1. So f1 is this formula. This allows me to calculate that my bn is related to my cn. Let me write that down. My bn is going to be the coefficient cn divided by the sinh of n pi b over a. And so I now know my b coefficient. Similarly, let's calculate what happens when y equals b. So when I have my y equals b, and I substitute that in, the second term is the sinh of 0, and the first term, y equals b, gives me sinh of n pi b over a. And we know that sinh of 0 is 0, so that term goes away, and I have the sine of n pi x times a number. On this boundary, we're supposed to equal f2, which we have its own Fourier series. And this allows me now to solve for my second expansion coefficient. It's the coefficient of f2 divided by the sinh of n pi b over a. Alright, what we still need to do though is we need to show that I have the same span, that I'm generating the same set of functions as I did with the exponentials. So let's think about the sinh of n pi y over a and the sinh of n pi b minus y over a. And let's see what those look like. The sinh is the exponential e to the positive term minus the exponential with a negative term. And so if and divide by 2, can't forget that. And so if I do this for both terms, let me just expand that. So when I have the positive exponent, I've split it into a product of two terms. And notice what I have. I have a linear combination. So I have a linear combination. I've got 1/2 e to the lambda y minus 1/2 e to the minus lambda y for my sinh. And for my second function, I have e to the lambda b over 2, e to the minus lambda y, and minus e to the minus lambda b over 2 times e to the positive lambda y. Okay, and so both of these functions are in the span. So I haven't left my space, but the question is, are they linearly independent? And that's going to be true because this determinant of their coefficients, 1/2 minus 1/2 minus e to the lambda b minus lambda b over 2 and e to the positive lambda b over 2. This determinant is not 0, which means I have a linearly independent linear combination. So we can use this new sinh of y and sinh of b minus y, and I can get the same space. We're ready to do an example now. So I'm going to think about a function. I'm choosing for my boundary condition a nice quadratic. The textbook has a nice triangle shape boundary condition. I'm going to do something a little different so you have two examples. You can look at the example in the book for one, and I'll do this one for a second. My choice of my f1 is such that at 0 and at a I have a root, and for f1 it's ax minus x squared. That's a parabola opening down, and so this has a nice quadratic shape. At the other boundary I have it going the other direction. It's the same formula, just with a negative sign, and so my boundary condition at the other side is the opposite. This has the advantage, by symmetry I can use the same calculation for my Fourier coefficients. So we need to calculate our expansion, right? We need to calculate the Fourier coefficient 2 over a integral from 0 to a of my function ax minus x squared times the sine of n pi x over a. We're going to call this our Fourier expansion coefficient for my function, and this second function is going to have the opposite, right? I'll just change the sign of all my coefficients. I don't want to do this integral by hand, so what we're going to do is we're going to ask Sage to do our calculation, and let me pull up the Sage code that we would use to do that. Alright, we've got two variables. We've got n and a, and so we will tell Sage that we have two variables. So that it can do the integral as much as possible, we'll tell Sage that our n is an integer through the first assumption. And it's just good practice. Our a is a positive number, so let's tell Sage to use that. Sometimes that's important in a calculation. So our coefficient, our bn, is 2 over a times the integral. Here's our function times sine of n pi x over a, and we're going to integrate x from 0 to a, and we'll ask Sage to show us the value of that coefficient. With a little simplification, here's the result I get. Right, so 4a squared over pi cubed, that's the same constant for everything. I've got a 1 minus negative 1 to the n. This must have come from a cosine of n pi, and divide by n cubed. Notice, by the way, that when n is even, I'll have 1 minus 1. This will be 0. This is only non-zero for n odd. So let's just make a note of that. Bn equals 0 if n is even. Alright. Well, we have our coefficients, and we know that our coefficient in the separation of variables expansion will be this coefficient times 1 over the sinh of n pi b over a. So let's do that. Let's go to MATLAB now. I want to see what this looks like. So here's a script that will implement our boundary value problem for the potential equation in MATLAB. And so let's think through this process. Once I do a calculation numerically, I need to have values for all of my coefficients or my parameters. So I'm going to set my a equals 2. That's the width of my rectangle. My b equals 3. That'll be the height of my rectangle. We're going to create a grid. Let me quickly draw this picture of what we're trying to do. We've got a rectangle going from 0 to a and 0 to b. And we can't calculate numerically something everywhere on a grid, but what we can do is we can partition the grid into slices. And so this first calculation is creating a sequence for x, and that corresponds to the values 0, 0.1, 0.2, 0.3, and it'll keep counting until I get to a. The second line, y equals 0 to b, is going to be calculating the values for y going up this grid. And these are one-dimensional sequences, so let's comment on that. Alright. When I'm doing calculations in MATLAB, we want to let MATLAB do as many of the calculations simultaneously as we can. It's been optimized to be able to work with matrices and vectors. What I do on this next line creates a grid, a two-dimensional grid. So now what we're going to be doing is we're going to be creating a matrix of x and y. So my x and my y are going to be matrices, and it's going to use the values of the one-dimensional vectors to create values for x and y. And sort of the way that you want to think about this is my matrix X, and I can't remember if it's actually rows or columns, but I think x is going to have like all of the x values as columns, so 0.1, 0.1, 0.1, 0.1, and so on until I get to my last value, which was 2. 2, 2, 2. And the y matrix that comes out of this is going to have rows that are all the same. So the first row is 0, the second row is 0.1, 0.1, and the last row will be the b value. And these two matrices have the same size, so that I can do calculations if I do the calculation in the second row, second column, I have the second x and second y, and I can do a calculation in terms of those values. This gives us the advantage of I can do my calculations for all values in the code at once. Alright, so where are we? Next, let's define a function that will calculate my Fourier coefficients. This is just for notational simplicity. FC is the name of my function. The at symbol in parentheses n means FC is defined as a function, and it has one element coming in, one argument, n, and then the formula that I give, that's the value of the function. And we use that down here in our loop. Alright, what we're going to do is we're going to create a new matrix, Z. Z is going to be the same size as both x and y, and so I fill it with zeros. This is an initialization, because what we're going to do is we're going to add one piece of the calculation at a time, so we have to start it at 0. Now we're going to calculate the first 20 coefficients, and I'm a little lazy. The even coefficients, they're all going to be 0, but I'll do this calculation anyway. It generalizes. You can use this for any example you need later. So we're going to do a sum as n goes from 1 to 20. The first calculation in the loop is doing it's the term that has the sinh of n pi y over a, and the second row we're going to add in the sinh of n pi b minus y over a. So we take our value we've calculated so far, and then here notice what we have. We've got our Fourier coefficient divided by sinh of n pi b over a times the sine times the sinh of y. Now, in MATLAB, there's a multiplication that's dot times. Similarly, there's a power dot power. This allows me to do calculations with matrices. Normally, multiplication of matrices would be matrix multiplication, and that's not what we want. So we're going to use dot times. I'm using ordinary multiplication because these are just numbers, but anytime I have a calculation that results in a matrix, so this is actually a matrix of values, this is a matrix of values, when we want to multiply those values, I need to do dot times instead of multiplying the matrices. Alright, once this script has gotten to this point, I have a matrix Z that represents the U value at each point on this grid. And I would like to see what that looks like, so we will ask MATLAB to generate two graphics for us. We tell it to create a figure. The first one will be a surface, and I give the matrices corresponding to the grid for x, the grid for y, and the value for my u, which in my code it's the z coordinate of my graph. I'd like to label my axes, and that'll generate one figure. And I also want to have a contour plot, so I'll generate a second figure using the contour f function. Same three coordinates, the x coordinate grid, the y coordinate grid, and the value of my function. By putting an f on the end, this is a filled contour plot, and it's going to make pretty colors. Alright, so let's take a look and see what the results are. Well, this is what MATLAB gave me. On the left you see the surface plot. So we have my x-axis goes from 0 to 2. My y-axis goes from 0 to 3. My z-axis, which is the value of my u function, gives me my plot. Looks like maybe I have my coefficients backwards here. At 0, my function is the parabola opening down. At 3 is the parabola opening up. So maybe I did put a minus sign in the wrong spot. And then I've got my contour plot. So these contour lines correspond to levels on the surface that are at the same height. And the color scheme is matching as well. So we get I'm 0 all along these edges. So this is 0. And I've got on this half I'm above z equals 0, and on this half I'm below z equals 0, or u, I guess. And we get these interesting contours. Alright, well, that's how we can use Fourier expansion to solve the potential equation, and I hope you have a good break.